Right, so in this video, we're going to look at some of the other rules, properties of exponents. Now, these aren't going to be quite as important to multiplying polynomials. Once we get into section 3.3, we're adding, and then 3.4, we're multiplying polynomials. So it's not going to be as necessary for that, but they are still good things to know. And they do come up if you're going into Math 105. So let's look at the quotient rule. The quotient rule says right here that if, as long as a is not 0 and m and m are integers, then a to the mth power divided by a to the n power is a to the m minus n. And while we're doing that, we're going to look at some other rules as well. So we're going to look at the negative exponent rule. This is basically saying, well, what happens to that if a to the mth gets canceled out and just turns into a 1? If this top gets turned into a 1, then we have 1 over a to the n. And notice that this would force m to be 0 and n, well, that's just a negative exponent. So negative exponent rule says a to the negative n is 1 over a to the n. And the zero exponent rule says a to the 0 power is just the number 1. So all three of these rules are sort of interlocked all together. And let me explain what's going on. First off, let's take a look at the quotient rule and what it's actually trying to get us to look at. So here's what's happening in the quotient rule. We have x to the 6th divided by x squared. Now, what that means, we've seen before, that means we have x times itself 6 times in the numerator of that fraction. So let me go out and write 6 factors of x in the numerator. If I can click correctly, 4, 5, 6. There you go. I got 6 factors of x and 2 factors of x in the denominator. Now, we should know that as long as x is not 0, because it's illegal mathematically to divide by 0 inside the real number system. So as long as x is not 0, then we're okay doing this. But what's going to happen is that this x here and this x here, those first two x's are going to be canceled out with these bottom two x's. All right. And then what's going to happen? Well, we're just left with 4 factors of x in the numerator. And then when things get canceled out in the denominator, that denominator just turns to 1. So what we end up with is just x to the 4th. Now notice what we did there. We're just subtracting 6 minus 2 and getting 4. We have 6 factors of x. We got rid of 2 of them. And so we ended up with 4 factors of x. Those 4 factors, because the numerator was a higher exponent, had a higher exponent than the denominator, those 4 factors ended up in our numerator. And there we go. Now, what's going to happen if there are more factors in our denominator? Well, I'm not going to go through the whole eliminating factors thing, but you can imagine that 9 factors in the numerator will cancel out with 9 factors in the denominator. That means there's going to be 6 factors left in the denominator. So 1 over y to the 6th would be the quotient rule version of this. All right. Now you may ask, you say, well, we're subtracting. It's always the bigger one minus the smaller, and then the factors are always going to end up in the bigger exponent's side. So here the bigger exponent on x was in the numerator, and therefore when we canceled out, factors of x are going to be left over in the numerator. Here, there were factors of x in the denominator. So when we canceled out, we had leftover factors of x. I said x. There are more factors of y in the denominator. So when you cancel out, the leftover factors of y will still be in the denominator. All right. Hopefully that all makes sense. And then notice that 1, when all things are canceled out, that just becomes a 1. When all things are canceled out, that just becomes a 1. And why we're getting a 1 there is because, remember, there's an omitted 1 coefficient that we're sort of ignoring in this situation. So if you factor out 9 factors of y, you're still left with that coefficient of 1. Cancel out 9 factors of y, left with that coefficient of 1. Now the quotient rule you can use in bigger settings too. So here we have 45x to the 8th times y to the 12th divided by 30x to the 18th y to the 5th. Now, remember what I said before when we dealt with power to power rule. You can't utilize the power to power rule if there's pluses and minuses in our expression. Well, the same thing is true with the quotient rule. Here, it's fine because 45x to the 8th, y to the 12th, everything's being multiplied in the numerator. And the same thing, everything's being multiplied in the denominator. If you had a plus or a minus, then you couldn't do this trick. So if this were 45 plus x to the 8th, this trick wouldn't work. So here's what we're going to do. We're going to rewrite this. We're going to think of this as 45 over 30 times x to the 8th divided by x to the 18th times y to the 12th divided by y to the 5th. Now, again, I can do that. I can rewrite this way only if everything is multiplied on top together and everything is multiplied on bottom together. All right. So if you have a plus, you're out of luck on this one. So 45 over 30, that's something you can plug into your calculator and have your calculator give you an answer for. As an improper fraction, that's going to be 3/2. So we're going to get 3/2 times, well, x to the 8th divided by x to the 18th, that's just the regular quotient rule. That's going to give me 1 over x to the 10th. So you subtract, there's more factors in the denominator, so 1 over x to the 10th. And then we end up with y to the 12th times y to the 5th. 12 minus 5 is 7, so you're going to get y to the 7th power. That one is going to be in the numerator. Now, when you do this, again, I'm trying to show all of the steps of how I think about it. But when you do this, you'll probably skip just to the very end and say, oh yeah, that's 3 times 1 times y to the 7th. That's going to be 3y to the 7th on top and 2x to the 10th on bottom. Okay, and once you get, again, used to doing all this middle step you'll probably skip. And this step you'll probably skip, and you'll just kind of say, oh, 45 over 30, that's 3/2. So we'll write 3 on top, 2 on bottom. X to the 8th over x to the 18th, that's x to the 10th on bottom. Y to the 12th over y to the 5th, that's y to the 7th on top. So that's the idea behind the quotient rule. So now we're going to look at the zero exponent rule. And basically this says, as long as a is not 0, then a to the 0th power has to be 1. Now, again, the reason a can't be 0 is that we don't want to have dividing by 0 like we did up here. It's very similar. We don't want to have 0 to the 0th power here. So as long as our base is not 0, then raising something to the 0th power is 1. So 7 to the 0th power, our rule says that has to be equal to 1. And by the way, why that says that, it's basically saying that we have no factors of 7. So if you want to think about it, it's like 1 times no factors of 7. No factors of 7 means you're never multiplying by 7. So you're taking 1 and not multiplying by 7, and you end up with a 1. All right. Now that's going to happen regardless of what your base is. As long as you have no factors of something, then you're going to end up as having a 1. So for instance, if we take negative 18 to the 0th power, that's no factors of 18. Excuse me, no factors of negative 18. So that's going to give us a 1. Now note that the negative sign here is inside the parentheses. That's going to be a big deal. So negative 18 to the 0th power is 1. And because we have no factors of negative 18. Now, when you go to the next problem, what you'll see is that we don't have parentheses around the negative 18. And this is a very important distinction because of the order of operations that we dealt with in our section like section 1, 2. And negative 18 to the 0th power is negative 1. Remember in section 1, 2, raising something, exponents came before multiplication. Well, that's why this happens. The negative 18 to the 0th power is the operation that's coming first. And so the 18 to the 0th power can be viewed as happening first, and then the negative is applied afterwards. Okay, so negative 18 to the 0th power without parentheses is different than when we put the negative 18 to the 0th power in parentheses. Okay, in fact, if you think about it, this is like negative 18, where the 18 to the 0th power is the thing that's in parentheses, and the negative sort of outside. The 0 power gets applied to the 18 first, and then we apply the negative sign there. All right, in the next problem, what we have is 13xy to the 6th, all to the raised to the 0th power. Well, it doesn't matter what our base is, as long as our base, whether it's 7 or whether it's something more complicated like 13xy to the 6th, whatever gets raised to the 0th power, as long as that thing inside there is not 0, is a 1. Now in this problem, we have 5 times 7n squared n to the 8th. The inside part getting raised to the 0th power is going to end up with a 1 as a 1, and then the 5 on the outside is going to stay. That 5 is not raised to the 0th power, so it stays. So you end up with 5 times 1, which is just 5. And there you go. So that's what the zero exponent rule is telling us. Things that get raised to the 0th power, as long as they're not 0 to the 0th power, get changed to a 1. But we do have to respect order of operations. Now, the negative exponent rule is the next rule that we're going to look at. And what that says is that, and we'll also look at the quotient to a negative power. It's very, very similar. But what the negative exponent rule says is that a to the negative n is 1 over a to the n. And so we're going to take a look at why this is. So let's take a look at this first expression here, 5 to the negative third. Now, by the negative exponent rule, that should be 1 over 5 to the third, which is 1 over 125. So what does that really tell us, and why do we get that 1 over 125? Well, if you think about it in the following way. So think about it as 5 to the third times 5 to the negative third. All right, let me write this down. Well, by the product rule, 5 to the third times 5 to the negative third has to be 5 to the 0th power, which we all know is 1. Right? Product rule says multiply, add the exponents. You end up with 5 to the 0th power, which we know is 1. So that means 5 to the negative third has to undo a 5 to the third. Now we know that 5 to the third is actually 125. Okay? And so what 5 to the negative third has to do is it has to be something that where you multiply it times 125 and it gives you a 1. So let's write that down. 125 times what would give us 1? Well, needs to times by 1 over 125 to give us 1. And therefore, 5 to the negative third has to be 1 over 125, which is just 1 over 5 to the third. So that's why that negative exponent rule has to be the way it is, all right, so that all of our other rules can work. Now, once we know that, then we can move on and just do the problems and understand what negative exponents really do is they put things that were in a top into the denominator. So x to the negative 8th is going to be 1 over x to the positive 8. And when I say puts things in the top, I'm just saying, to the bottom. So we're going to make a negative exponent on the top, a positive exponent, x to the 8th, on the bottom part of the fraction. So that's what those negative exponents do. And we don't have to go through all the rigmarole of going back through why that has to be. Now, the same thing is going to be true when we have a negative exponent in the denominator. When you have a negative exponent in the denominator, like 1 over d to the negative 4th, what happens is you get a d to the positive 4 in the numerator. Now, I'm not writing d to the 4th over 1. I'm just writing d to the 4th because that's how we go. So, and that's for the same reason that we had earlier. Now, a lot of times we want to write things where all of our exponents are positive, and you can see here that x to the negative 5th is a negative exponent. So in mathematics, we like to write things with positive exponents. And so in this case, what we can do is we can take this 7. 7 is like having a 7 to the first. The x to the negative 5 part that I just highlighted, that is our problem spot. So we can change that just like we did x to the negative 8th. But what's going to happen to the 7 and the y to the third? Well, 7 is like having a 7 to the first power. So we can keep that on top because we have this, again, like a 7 to the first power. Let me write that down. All right. So if this were a negative 7, that would still stay on top because the only thing we care about is positive exponents. We don't care about positive coefficients. So if we had a negative coefficient, that wouldn't make any difference. The only difference, the only thing that we switch is when we have a negative exponent. Like x to the negative 5th is going to switch to an x to the 5th in the denominator. Y to the third already has a positive exponent, so that's going to keep as y to the third in the numerator here. All right. And you can think of this as switching from numerators to denominators the whole time. And you can think of 7x to the negative 5, y to the third as like 7x to the negative 5, y to the third all over 1. Okay. And then think of the x to the negative 5, that negative exponent gets put in as a positive exponent when you take things to denominators. So switch from numerator to denominator, and there we go. So I'm not going to write that in general, but that's kind of what's happening. All right. Switching negative exponents, take things in our denominator like d to the negative fourth, put them in our numerator as d to the positive fourth. And x to the negative eighth in our numerator takes and puts it into the denominator as x to the positive 8. Now, a quotient to a negative power is essentially doing that. It's saying that if you have a fraction raised to a negative power, well, we know negative power switches numerators and denominators. And so if you switch numerators and denominators, we can take that power and make it a positive one. So if we flip the denominator to the numerator and the numerator to the denominator, we can change the power from a negative to a positive. Again, this is all when I do not have a and b as zeros because you don't want to divide by 0. All right, we're not going to deal with types of that problems because we're going to go right into section 3.2 instructor-led problems.